Hey, what's up, guys? So I'm gonna go ahead and go over problem number 9 on problem number 1 on discussion 9, last week's discussion. It was kind of a hard problem. A lot of you guys had quite a bit of difficulty with it, so I decided I'm just gonna go over it step by step, and hopefully this video helps. So the first thing I'm gonna do is go over how to think about these kind of problems. So the first thought is we have some sort of double slit experiment. You guys have probably all been in lab already, so you have some light that comes in through here. Right, it comes in through here at any angle, doesn't really matter. Let's say straight, and then it diffracts, so it goes all over the place. But it actually, interferes and constructs in such a way as to create these. Let me see if I can actually draw these in. Oh, that's a horrible. I couldn't possibly have chosen a worse color to create these like bright spots. Right, you guys have seen that, and then they're called m=1, m=2. So we have a pretty difficult problem here that tells us that we have these, you guys should probably take out your worksheet with you. You should hold your discussion worksheet while you watch this, just because I don't have it all written down, but it tells you the difference, like the physical distance between the m=3 and m=2 bright spot in this problem is 3 centimeters. Okay, so that's the difference between the m=3 and m=2 bright spot, not from the m=0 to m=3. That's very important. So you have that distance. You're also given the fact that the screen where all these bright spots are is 3 meters away from where the light was entered. Okay, cool. So a lot of you had the first instinct, I guess, to try to use tangent of theta or some sort of theta, with this being like the opposite and this being the adjacent, and then finding some sort of value there. You actually can't do that, because if you analyze it pretty closely, the angle, the line, I mean the distance that is given doesn't form a right triangle with any other values. And obviously tangent, sine, and cosine only work with right triangles, back from trig class. So in this case, we have to be a little bit more creative in how we do this problem. So the first thing that I'm going to do is break this problem up into two separate triangles. Two separate triangles that is going to make my life a lot easier and make my calculations, well, I guess, possible, right? So in this case, this is, oh my god, this pen sucks. So this is one triangle right here, all the way down to here. That's one triangle, whatever that is, okay? So that's one triangle. And the second triangle is just the bigger one, the one that goes all the way up and all the way down, right? So this triangle. Okay, so we're gonna find those two triangles first. So the first step here is to use our, good old-fashioned trig functions. So we can actually use tangent because we have the opposites and we have the adjacents. And when I say we have, I don't mean with actual numbers. I know it sucks, but we're gonna have to use variables here. So we can do tangent of theta 2 is equal to y2, and I'm defining y2 as being the distance from the m=2 spot down to 0, so the entire height, divided by 3 meters. And then I'm going to say the tangent of theta 3 is equal to y3 over, again, 3 meters. And now we have an interesting relationship here. I'm actually going to do this first. Actually, before I go there, I'm going to mention one quick thing. I know you guys were actually told in class, because Professor Neiman told me this, that he actually said not to approximate sine and tangent theta. He told you not to do that. And he's right. I mean, of course, he's the professor, listen to him. But in this case, we're actually going to have to approximate sine theta for tangent theta, because it's the only way we can do this problem. And also because, if you notice, this is 3 meters of a distance, right, from the entrance to the exit to the wall. And this distance over here is 3 centimeters. And if you were to go, okay, there's 3 of those bright spots, all are roughly the same. It's about 10 centimeters. These are going to be some tiny angles formed by 3 meter long distance and a 10 centimeter height, right? So at very, very small angles, you can actually approximate sine theta equals tangent theta. So I'm actually going to replace this real quick with sine theta 2 is equal to y2 over 3 meters, and sine of theta 3 is equal to y3 over 3 meters, okay? Now, here's where it gets interesting. We have to notice a relationship here. I actually already drew it. See this red height and this blue height. The difference between those is going to be this height, right? That's the difference between the blue and the red height. So the blue height is sine theta, is this height right here, and the red height is this one. So the difference between those two is actually going to give us that green height, the one that we're already given. Do you see where we're kind of going with this? So we're going to use that relationship to finally get us a workable number. So I'm going to say y3 minus y2 is equal to 0.03. I just converted 3 centimeters to meters over here. Okay, so and this is delta y. So, and that's going to equal what? So let me actually rearrange this a little bit. If I bring this 3 meters over to this sine theta 2 side, I can just say that y2 is equal to sine theta 2 times 3, right? So in this case, since I'm doing 3 minus 2, let's do 3 times sine theta 3. So this is an equal sign, equals 3 times sine theta 3 minus 3 times sine theta 2. Now here's probably, I'd argue, the hardest part of the problem. The hardest part is seeing the relationship, because once you're here, you still don't have much to solve with, right? Because all you have is this number and you don't have sine theta or sine theta 2. But we can use this relationship to solve for sine and then just plug in these variables for sine. So sine theta is going to be 3 times m3 lambda divided by d. I just substituted m lambda over d for sine theta. Minus, over here we have 3m2 lambda over d. And all of that is equal to 0.03. Now, I can factor out a few things because d, 3, and lambda are all going to be the same. D is obviously the same because, I mean, it's the double slit where they all originated from, so that's, that's constant. Lambda is also constant because, I mean, you plug you put in one certain type of light in there, right? Maybe it's a red light, a green light, doesn't really matter, but it's the same wavelength light. And 3 is obviously just a constant. So I'm going to go ahead and factor that out. Let me scroll down a little bit. So you have 0.03 is equal to 3 lambda divided by d times m3 minus m2. And if you notice, m3 and m2 are going to give you, well, the values of those are 3 and 2 respectively. It was kind of convenient with those subscripts. And so 3 minus 2 is going to be 1. Okay, so 3 minus 2 is going to be 1, so we can kind of cancel this part out, so it's not really interesting anymore. I mean, now we have 0.03 times d. I'm bringing this over to the other side, dividing by 3, and that's going to give us our wavelength, which is what we were looking for. Let me just make sure my algebra is right. Yes, it is right, and this is going to give you around 666. It's actually going to give you 660, but it should be 666, which is why you might see that in the solutions, only because I think the diffraction grading was 0.666666 and repeating, so I just, I rounded at some point, but it should be around 660 nanometers. I'll save the calculations for you to do, okay? And then now let's move on to part B. I'm actually going to put a timestamp on for this problem, just so people can stop watching here, because part B through D are honestly pretty easy. So B, I'm not going to go over much, but it's asking what happens to theta when the distance between the slits increases, aka when the diffraction grading gets smaller. So if D gets smaller, the wavelength theta has to get bigger, right? So that's pretty easy. They're just an inverse relationship, down, up. Okay, now I'm going to go over part C real quick. Part C says on a very, very large and distant screen, how many total bright maxima will there be? So for this problem, we have to write d sine theta equals m lambda. And it's asking us on a very, very large and distant screen, how many total bright maxima will there be? Well, what can we maximize here? This is just, it's a given diffraction grading. We can't change that, so that's going to be constant. And then sine theta, okay, let's think about that. Maybe we can, increase that angle. Maybe that angle gets increased, I'm not sure. M, well, that's kind of what we're looking for. And lambda is not going to change because, again, we're shooting one type of light in there. So let's go ahead and solve for M. We get d sine theta over lambda. We have our lambda now, right? We have our lambda. We have our diffraction grading. Our diffraction grading is, I believe, what did I write up there? 6.6 times 10 to the negative 5. 6.6 times 10 to the negative 5 times sine of theta. Oh, well, I'll leave that part blank for now, divided by 660 times 10 to the negative 9. And then our sine theta should be what? What should our sine theta be? In this case, our sine theta should actually be 90 degrees. Right? Should be 90 degrees. So plug in 1. Sine of 90 degrees is 1. Sorry, I was looking over to my other computer just to make sure some stuff. So that's 1. And then if you solve for this, you should get, I think, about 100. Yeah, you should get 100. You might get 100 point something, And if you get something above, like if you get something like 100.3, the maximum is obviously 100 because 0.3 is essentially meaningless, right? You need only integers of n. So that equals m, and then you have to multiply that by 2 because we only found everything above here, right, on the top part. So you have to multiply that by 2 and you get 200. And be careful because on an exam you're still not done because you're forgetting that m equals 0 is not accounted for in that. So it's actually plus 1, oops. So it's actually plus 1 more, so it should be 201 bright spots, okay? And then for part B, it's saying at what angle will the bright fringe that is most distant from the central bright fringe occur? Honestly, that question's kind of longer than it has to be, but what it's basically saying is, what is the angle at which the furthest one appears? And again, that kind of relates back to this sort of thought process we had here. It's when sine theta, it's when the angle is equal to 90 degrees. Because that is the largest possible angle that you could possibly go up to. That's not 90 degrees, but I'm trying to show you that anything past 90 degrees is going to go backwards, and that's not really possible. Technically, even 90 is not possible. Okay, so 90 degrees isn't even possible. It's everything less than or equal to, no, not equal to, less than 90 degrees. Okay, so approaching 90 degrees. That's the idea. All right. So I hope you bared with me in my stuttering and mumbling, but that's how you do this problem, and I hope that helped, okay? I'll go ahead and write timestamps on the bottom of the problem for this. All right, guys, thanks for watching, and good luck on finals. I hope everyone doesn't study too hard and has a successful end of the quarter.